Good morning, everybody. My name is Michael Szyminski, and I'm here to talk to you guys about acoustic sensory telemetry. Acoustic sensory telemetry is the integration of water quality sensing and acoustic telemetry. So let's talk about acoustic telemetry first. At its basis, it's a way of remotely collecting information on aquatic organisms. It's a system that comprises a tag or transmitter that's attached or surgically implanted into an aquatic organism. Then the tag sends acoustic signals to a receiver which relate movement, presence or absence, or behavior of the aquatic organism. And the receiver can either be stationary or it can be tracking the animal as well. Now, as the signal moves from the tag to the receiver, and the reason it has to be an acoustic signal is because, and specifically an ultrasonic signal, so ultrasonic frequency between 20 to 500 kilohertz, is because anything else is going to get absorbed in the water, which is why radio waves don't work underwater that well. In any case, the first step is for a transducer in the tag to convert the signal from electrical to acoustic. Once it's an acoustic, it can move through the water to the receiver. Signal moves through the water to the receiver, hits the receiver. Receiver has a transducer that converts it back to electrical, and it can start storing that information. Signals we usually call pulses or pings, and just like any other message, they have fixed components and variable components. The fixed components help it be recognized by the receiver, and they are amplitude, pulse length, and phase. You can't really vary those, but what you can vary are the rates of pulsing and the number of pulses that you have, and this gives us two different ways to send a code or signal. There's continuous signaling, which is just really simple. It's pretty much only useful for following one tag or one fish, and it's on fixed intervals. And it can be used to locate the fish if you compare the known spacing between each pulse with the lag time that you're getting in between each pulse. And the more receivers you have, the better idea you have of the positioning. You can start getting into kind of 3 dimensions. But coded signals employ a little bit of a different method of communication. It's more of like barcode, so there's different number of pulses in small bursts, and there's different spacing, which means that you can start following more than one fish. You can have multiple tags because you can store a unique ID tag, and you can start storing information on physical properties if you can get it. This is where acoustic sensory telemetry jumps in, because now there's a way to communicate information about the physical world. Right now, what we have is 2 sensors basically available. We have one to measure the depth and one to measure temperature. And the temperature uses a thermistor, which is a resistor with temperature changing resistance, and the depth is measured using a miniature strain gauge. Also, the resistance changes based on the pressure, which you can relate to depth. But what we're starting to see is this really big growth or expansion into different sensors. So one that's being worked on in McGill is a fluorescence spectroscopic sensor, which can be used to identify or quantify dissolved oxygen. And this is really cool because you usually only see this stuff in the lab. But how it works, or how it's proposed to work, is that this material called Zerogel, super light, really small, is going to have water go into tiny cavities, and then LED lights are going to flash, and based on the amount of fluorescence, every compound and element has a different level of fluorescence, you're going to be able to identify different compounds. And there's also colorimetric sensors that are coming out. And this is huge for acoustic telemetry because up till now you were only able to get that movement, presence, absence, or even just depth and temperature. So I just wanted to outline one example where this would be really, really useful. There was a sockeye salmon study in Fraser River in BC, 2010. And this was a 15-year study on sockeye salmon movement in relation to algal blooms. And what they ended up finding was that algal blooms inversely correlate to fish survival. But what they had to do is that they had to use telemetric tags, like huge amounts of them, huge amounts of receivers to follow these fish around. And then they had to also go in the field and sample water and figure out what the physical properties were. But if they were able to use acoustic sensory telemetry, they would be able to get readings right at the fish and see really intimately what is happening exactly where those fish are. And if you're doing sort of like an avoidance study or a presence-absence study, it's really vital to know what's going on right where that fish is located. And this is mirrored in almost every single telemetric study. They would all benefit so much from acoustic sensory telemetry. So thank you guys for listening. hopefully it wasn't too rushed, and if you have any questions, I would love to hear them.